Now we are going to turn our attention to quantity that is extremely important in the mathematical modeling of infectious diseases. This quantity is called the reproductive number. And there is certainly a depth of technical level to carry out calculations to compute this quantity from a mathematical model described by a system of ordinary differential equations. But before we take that route of computing and calculating this quantity, I would like to spend some time motivating with the context of in many compartmental models, this calculation reduces to a computation that involves the computation of eigenvalues of a matrix. For models that are described in continuous time, there are generalizations on the definition of the basic reproductive number, and this will involve sophisticated integrals, and especially when you have models with age structure, on a continuous scale, and some other type of model described by integrals or kernels or things of that sort. So there are generalizations on the definition of the basic reproductive number, but I first like to motivate with something that is very concrete in the context of matrix models. Okay, so before we talk in specific detail on an operator, we are going to spend some time connecting with material that you were briefed on recently that has to do with matrix models. Okay, so now we're going to use a matrix model to describe the evolution of infection in a population, and we're going to make a distinction as to we want to consider stages of infection. Okay, so I think originally we had used when we wrote a model that looked like this, S going into I, right? We only had one compartment where we were collecting all individuals that are carrying the pathogen that produces the infection. And that one compartment was called I, was denoted with the letter I. So now imagine, okay, this is good for the beginning, but now imagine there are compartments I sub 1, I sub 2, I sub 3, and there is a lot of them all the way through I sub m. Okay, so now imagine that we can group individuals that are infected, but we can label the levels of infection in something that I'm calling here infection stages, okay? And then we can label those stages with, numbers 1 through m, discrete numbers, okay? So if you only had 2 of those stages, that's a very common example. If there is only 2 of those, then you could say this stage here has to do with incubation, okay, or sometimes this is what you call the stage in which individuals are infected. They actually are hosting the pathogen. They have been exposed to the pathogen or infectious agents. However, they first undergo this stage in which, while they have the pathogen, they are still not capable of passing on the pathogen, and that capability comes at another stage that is called the infectious. So here they are infectious. Okay, they are infectious over there. It almost doesn't fit. Anyway, so this would be I sub 1 is what we'll call exposed, and then I sub 2 is what is called the infectious stage, right? So this is an example in which there are 2 of these. In general, you can say there are m infection stages when m equals 2. I think we briefly discussed a model before that looked like S, E, I, R. And then we were saying you can go from S to E, from E to I, from I to R. Okay? And so definitely in this model, these two stages are stages in which individuals are infected, but is the second stage here that denotes that group of individuals that are capable of passing on infection. Okay, so that's the context we're working with. And now we're gonna formulate this in terms of a matrix model where okay, so let's suppose that we have a matrix. Here, this matrix is denoted by the letter K. So this matrix is square. It has m rows and m columns. So here is K, and K looks like a square. Okay, so there are m rows and m columns. Typically, you say that any entry here and this matrix, well, that looks, maybe I should do another entry. So maybe one entry here that looks kind of like this. Okay, you can say this is the I column, this is this is the I row, and that is the J column. So you would say this entry there in general is K sub I J. Okay, that's a very common way of describing entries of a matrix. And we call this matrix the next generation matrix. Okay, you'll see why in just a second. We are interested in using this matrix for a model that has this form. Basically, the next, here the time steps are denoted by n. N denotes the time unit, and this model describes the time evolution of infected individuals. So this is telling us that we can approximate the time evolution of the infected population of all stages of infection. We can approximate that process with a simple matrix model that we basically know everything there is to know about this model. So here the entries of the next generation matrix denote the average number of new infections. Okay, every entry on row I, column J, denotes the number of new average number of new infections in stage I from infections that are originated from stage J. Okay, so this labeling of the IJ entry of the next generation matrix has a meaning. Okay, it has the meaning that that number of new infections on a particular location is produced or is generated from infections at another stage. Okay, so the time scale here, the time step is denoted with n, right? And these are discrete time steps. And the fact that they are discrete, the fact they are integer numbers, and they have step size. Okay, so the time step here, it's going to be connected to the so-called generation. But so you would like to think of this process in terms of offspring. Okay, you like to think of this process as the population of infected individuals, which are now distributed or grouped into these stages of infection, and how those stages of infection are progressing with time. But in the context of infection, the offspring, right? If this were in the context of a population of animals, and these were described, and these type of matrix models are very common to describe populations of species or animals, for example, where the stages, 1, 2, 3 stages, are a simple way of describing 3 types of, say, age groups, for example, right? And so you can think of babies, and then juveniles, and then adults. Maybe 4 groups. You can have elders, right? This is a very common way of describing, I don't know, populations of whales or some type of reptiles and stuff, things of that sort. So what matters in that context of ecology, of theoretical ecology, is to simply describe the time evolution on the female of that species, because the females are the only ones capable of producing offspring, and the offspring is what keeps the population evolving over time. So here the analogy is very similar. Instead of describing the evolution of reptiles or whales or turtles or something like that, we are paying attention. We are making the center stage here. This state variable x is keeping track of the number of infected individuals along all stages, right? So this x at time n, or time n plus 1, is a vector that has m entries, m components, okay? And so the evolution here is described not necessarily on typical time units such as, days or minutes or weeks or years, but rather on generations of infected individuals. And so you would like to, with this type of model, think of this process as infected individuals producing babies, but they're not literally babies, they are offspring of infections. So every time an infected individual in a particular stage, J, for example, is capable of producing an infected individual in stage I, that production is considered infection offspring, and that's precisely what this type of matrix model describes, and it's actually a very common way of describing that time evolution. Okay, and there are some technical parts here about the generation time of infection, and the scale here is not necessarily every 1 day or every 60 minutes or every 24 hours. These models are the conceptual understanding here, the heuristic understanding is that the time scale is describing generations of infections, and this is not necessarily of the same length, but the magnitude should be consistent with the infectious period. So what is the infectious period? This is the length of time an individual remains capable of passing on the infection. Okay, for certain diseases, this infectious period is something in the order of days, 2 or 3 days. Some other diseases would have an infectious period that may be on the order of weeks, maybe 1 week or maybe 2 weeks. Okay, but certainly the infectious period is not going to be, well, anyway, so that gives you an idea of the magnitude. Okay, and so what we're saying with this type of formulation here is that when you iterate this model, right, the iteration of the model means that you take the matrix and multiply the matrix by a vector. So you have the vector from the previous time step, right? So what the operation that is going on there is a matrix operation. You have a square matrix K, you multiply that matrix by a vector, and this, remember, this is m rows, m columns, and this vector is m by 1. This is giving you a vector, which is m by 1. And this vector is your new update. That vector would be the vector with the number of individuals on every stage of infection at the next time step. But what is the meaning of that vector x of n, or x of n plus 1? Well, the jth component, okay, so the jth component, in other words, x sub j at time n, that jth component is describing the number of infection cases in stage j at generation n. Okay, j takes values between 1 through m, but here n is the step, is the time step, is the generation. So you have generation 0, which are the initial conditions, generation 1, generation 3, generation 4. So think about generation versus, when we're talking about time, think about yourself, your family, right? And think about generation versus other time units. For example, I am 39 years old. So every year I celebrate my birthday. That's a celebration remembering when I was born. So there is the time scale of 365 days, 52 weeks, 12 months. They're all equal to 1 year. And every 1 year, basically now for 39 times in a row, then I remember that I was born on a particular date. However, I am a member of one generation. In my family, I am a member of three. My mother had offspring equal to three individuals, right? So I have one sister and one brother. The three of us belong to one generation, okay? So even though I am 39 years old, my sister is 35, and my brother is 30, and this is a substantial number of years for each of us. It doesn't matter how many years. I mean, this is 39, but if you say in days, this is 39 times 365. That's a large number, right? And similar for 35 times 365 or 30 times 365. Those are large numbers. And if you multiply that by minutes, I mean, this is a substantial amount of time. However, I only count for one generation in my family. So my mother and my father could be considered generation 0. Their offspring, my sister, brother, and myself, we are generation 1. My brother has one daughter, and my sister has one daughter. So those are my nieces, and they are members of generation 2. 20 years from now, my nieces, or maybe there will be more, 20-something years from now, my children and my nieces and nephews will have other children. They will be members of generation 3. So we have generation 0, generation 1, generation 2, and generation 3. As you can see, 3 generations can really extend over time units that are quite significant, right? There could be stretches of 10, 20, 30, 40 years, right? And all those stretches are within one generation. Okay, so just keep that in mind. Now, so we're gonna talk about some mathematics here. Some of these things are fascinating. We had already seen in action the power of eigenvalues of a matrix, and how relevant eigenvalues on a matrix are for computing powers of a matrix, and how relevant these eigenvalues are in matrix models. So this is basically going back to some of those facts. Now, then these are technical considerations, right? This is something that you really want to review here, your linear algebra. Okay. These concepts of eigenvalues and eigenvectors, you really want to be fresh and up to date on those concepts. Another concept you really want to be fresh about is this thing: linear independence. And here is another buzzword here: singularity or non-singularity. So when a matrix is not singular, there is a plethora of properties that are equivalent. What it means to be non-singular versus to have a non-zero determinant versus to reduce to the identity matrix versus to have an inverse versus to have full rank, which means the matrix itself has columns that are linearly independent, and that means that those columns, linearly independent columns, are a basis of a subspace. There is a number of things there. And so if we make an assumption, if we say, suppose that the next generation matrix is non-singular, that is a strong assumption. That is no free lunch. Okay, so that is something that it is substantial. Okay, So what I'm going to discuss here, I chose to discuss this making this assumption, but bear in mind that there's a whole branch of mathematics called linear algebra, and then there is another branch called numerical linear algebra, which is also fascinating. It's very hands-on and is motivated by very realistic real-world problems. Numerical linear algebra. So not every matrix is non-singular. There's certainly a lot of matrices that are non-singular. Some matrices are near singular, okay? And but anyway, so if we assume, for the sake of this argument that we're gonna make, that I'm gonna go through, let's assume that the next generation matrix is non-singular, meaning that among many properties, the next generation matrix is going to have eigenvectors that are linearly independent. That means that it is possible to write that matrix in a factorization. In other words, we would be writing that K, which itself is square, can be written as a square matrix times a diagonal matrix times a square matrix. Okay? That is the idea of the factorization. This factorization is beautiful. It's and this square matrix here stores the columns of this matrix S are the eigenvectors, and so the columns of S inverse. Well, anyway, so that's how you compute S inverse. But then the matrix in the middle, this lambda, is a diagonal matrix. Diagonal means there are zeros here, there are zeros over there. Now it looks like a percentage sign or something, but this is the structure. Okay, so what happens if this is the assumption we make? Well, if that is the assumption, if K can be factored in terms of the matrix storing eigenvectors, which I'm going to call the eigenvector matrix, and in terms of the eigenvalue matrix, the matrix storing the eigenvalues on the diagonal, if that is the case, then we can write the solution of the matrix model. So the matrix model is this. We iterate, right? At every time step, we take the matrix and multiply that matrix by a column vector, and that matrix column vector multiplication itself gives a new vector, and that is the updated vector we're interested in, right? So that model, the matrix model, with this initial condition, has this solution. Okay, is the nth power of the next generation matrix multiplied by the initial condition being a vector. Okay, now what happens? Well, if the matrix is diagonalizable, meaning that you can write K as the multiplication of S times lambda times S inverse, then taking the powers of K, and this is something we had previously discussed, reduces to simply taking the powers here of each of those eigenvalues. Okay, taking the powers of the entire matrix is basically reduced to raising to a power each of the eigenvalues. Okay, so what we'd like to argue here, so and let me just switch gears. What we would like to argue is the following. So let's say we have this model. I'm sort of new with this, so you're gonna have to bear with me. So what we're saying is we have x at n plus 1 is k times x is k times x at n, and we're saying that we know the solution of this being k to the n times the initial condition, but that we can write this as s times lambda, capital lambda to the n times s inverse times the initial condition, this being x bar 0, something like that. Okay, so here the important thing is that lambda n is a diagonal matrix that has lambda 1 to the n, lambda 2 to the n, all the way through lambda m to the n. In other words, this matrix looks like lambda 1 to the n, and then 0, 0, 0, 0, and then lambda 2 to the n, and then another bunch of zeros here, and across the diagonal this becomes here on entry mm. This is lambda m raised to the nth power, and there are all zeros above the diagonal, all zeros below the main diagonal. Okay, that's what that lambda to the nth looks like. So the important thing, well, one important thing is to ask, what is the role played by what is the role played by lambda sub j? Okay, what is the role played by the distance, by the modulus of lambda sub j in xn? What we're interested in is on the solution. This is the solution of the matrix model describing the process. Here is the process of infection. Okay, so the behavior of this solution is influenced by the nth powers of the eigenvalue matrix. So we're wondering, okay, if we know information on the modulus of every eigenvalue. So I said something about lambda j here. Maybe I should say that j goes from 1 through m, right? That's for any j. So what is the role played by the modulus of the eigenvalue on the solution of that matrix model? Okay, so that means that we're gonna look, I want you to start visualizing this in the following way. Let's suppose, we have m eigenvalues. I'm just drawing a picture. Suppose m is equal 4, okay? So that we can look at this picture. The eigenvalues in general, every lambda j is a complex number. Every lambda j resides on the complex plane, okay? In general. Now, this is a scenario that we have here in a sketch of the location of lambda 1, lambda 2, and lambda 3 in the complex plane. So in the complex plane, which is C with, looks like a moon or something, C with a fancy, this means the complex plane. You can think of this plane, you have the horizontal axis, which contains that horizontal axis here is called real axis, and you have the vertical axis called imaginary axis. So every element of this plane, let's say for example here is lambda 1, that lambda 1 has the real part of lambda 1 on the horizontal axis, and then the imaginary part of lambda 1 on the vertical axis. So every element of this plane is going to have a coordinate on the real axis and another coordinate on the imaginary axis. Here's lambda 3, and here is lambda 4. So each of those, lambda 1, lambda 2, and lambda 3, are elements of the complex plane, and they each have a component in the real axis and a component in the imaginary axis. Now, the modulus. So the modulus is what is measuring. We use the modulus, for example, for lambda 1. The distance from the origin in this plane is measured by the modulus. This would be the modulus of lambda 1. We now take here and measure the distance of lambda 2 through the origin. So this would be modulus of lambda 2. Okay, and say this here would be the modulus of lambda 3, and from here we measure the distance to lambda 4. This would be the modulus of lambda 4. Okay, so the modulus is a generalization of the so-called absolute value. So I'm going to write a note here. The modulus, in general, we say lambda j, And you can, if you didn't know this was a complex number, you would say that's the absolute value of lambda j. Well, in this context, we don't call it absolute value. It's absolute value in spirit, the same spirit. So here we call this modulus. And the modulus of lambda j is measuring, is quantifying the distance of the distance between the complex number in the plane to the origin. So this is the distance from the origin, and the origin is 0 plus I times 0. In other words, 0, 0. That origin there has a real part equals 0 and has an imaginary part equals 0. Okay, that is the so-called origin. So, as you could argue in this sketch here, is that with this visualization, that's why I only draw 4 of eigenvalues. But you can argue that even with this representation, and even with I'm not giving you exactly any precise information as to what is exactly the real part, what is exactly the imaginary part, but just by looking at this figure, we can pin down, we can say which is the eigenvalue that has the largest modulus. And in this case, the eigenvalue with the largest modulus, and I'm gonna maybe draw on top of this again, according to my sketch here, that eigenvalue would be lambda 4. So this distance here, even though it looks very similar to the distance, it looks very similar to the distance of lambda 2 and lambda 3, this distance for lambda 4 is largest. Okay, that distance is largest. That's gonna be important. So lambda 4 has, in this example, in this pictorial representation, this distance is the largest of the 4, okay? And that is going to be important because with the largest distance, centering, taking center at, taking center at the origin, you can picture as we can draw a circle. Okay, so we can draw a circle, not the best circle of all, but this certainly is not something that would fit here in the sketch that I'm doing, but it would be something that looks like that. So this is a representation of a circle with radius modulus of lambda 4, okay, and center center at 0, okay. This circle with radius equal to the modulus of lambda 4 and center at 0. This circle contains all eigenvalues. Okay, so if we identify which eigenvalue has largest modulus, then we have this notion of encircling, okay, taking center at the origin and taking a radius equal to the distance, to the largest distance from the origin, and that guarantees that this circle now will contain all the eigenvalues, okay? It will contain all the eigenvalues. So there is, in this context, there is something called a spectrum, okay? And more importantly, spectral radius. The spectral radius. Remember, we're working with the diagonal matrix lambda, which looks like this. This is lambda 1 all the way through lambda m, right? There are zeros over there. And then we're going to define this with this notation, rho of lambda. Rho of lambda is going to be the maximum of the modulus of all eigenvalues. So this is in notation now. In mathematical notation, this is describing what we just sketched previously. So you consider the modulus of every eigenvalue and find the one eigenvalue that has largest. So you're really maximizing modulus and identified which of those has largest value. Modulus is distance, so modulus is a non-negative real number. And so with this definition, we're going to say that rho of lambda, the spectral rho of lambda, the maximum or the largest modulus, this is called the spectral radius. And the reasons for calling this spectral radius are precisely on the previous illustration, in which if you now define this as a radius of a circle that's centered at the origin, then that circle will contain the entire spectrum, which is another name for the set of eigenvalues. Okay? So, we're going to take, I think this conversation will be continued. We have to talk about matrix norms, but we're going to pause here for a minute.